Okay. Hey guys, we're back with 6.3 here. We only got this section and one more to go left in our year before we're wrapping things up. What a crazy couple of days it's been here. In a lot of ways. Hopefully, everyone is staying safe and sound here in Syracuse. I think I want to have another Zoom meeting later this week to answer any questions on pretty much anything that you guys may be having right now. I'll post that in probably like a talking points tomorrow, or maybe in the comments here is probably even a better idea. With all that being said, let's get looking at this section here, which is called Volume by Cylindrical Shells. We could start off with a question that looks pretty harmless, kind of like they did in 6.2, which was 2 weeks ago at this point, or like a week and a half. And it could say, find the volume of the solid obtained by rotating about the y-axis the region bounded by y equals 2x squared minus x to the third, and y equals 0. That would get us some region that kind of looks like this little hump here. I know it goes through at 0, 0, and 2, 2. The reason I know that is you can kind of take this equation, since it's also bounded by y squared, set it equal to 0. We can pull out an x squared. And so 0 and 2 are options here. And we're rotating it around the y-axis. So if we're thinking last time, that's probably an indicator that we're going to do this with respect to y all of a sudden, which means you need to have things in terms of x equals. However, the issue here is if you take this equation and try to solve for x equals, there's a problem here. It really can't be done. There's no nice x equals here, because if you think of that in that sense, x equals, it's not going to be a function anymore. So we actually, in fact, can't solve naturally for that, which then brings us to this huge roadblock here. And you may be thinking, well, let's also think of it this way. Remember last time we would take this and just kind of cut it through, and we'd be looking at like this washer that's over here. But then if we tried to identify like the smaller to the bigger radius, notice it is just one function. How can we both have the small radius and the big radius be the same exact thing? And the answer is that doesn't really happen. These are all issues saying that we can't do it in the way that we normally were doing it. And we actually have to look at a brand new method here, and it's called shell method. And so the shell method is when you come into all of these roadblocks to try to do something, think of it kind of like those stacking cups, or like the old Russian dolls, like the stacking nesting Russian dolls, where one just kind of goes inside of another and it builds its way up. That's what's going on here. To kind of give you an example, a textbook has a great shot of it here. If we wanted to find the exact area of some thing like this, it's kind of like a bundt cake. You can take a bunch of these shells and stack them together, and as we get an infinite number of them, it actually gets us the exact volume that we're looking for. But let's start with identifying just one here. So think of this as like some tube, think of it like a toilet paper roll or something, and let's say we were going to kind of cut this. So we take this, and it is just some kind of cylinder. But if we cut it open, and we're going to cut it open very specifically. So let's say we're cutting the seam right down here and unraveling it. The shape that we're ending up with is going to be a rectangle of some sorts. And we can actually easily define this rectangle and find the area of it. And so what we're thinking is the height of this is going to be whatever the height of this one function is. So that's our function's height. Right, so think no matter where we are down here, even if we had kind of a smaller one here, how high that cylinder is just the function's height. Okay, that's not so bad. Now we're trying to think what this whole thing is. And it's a circle. And what's the circumference of a circle? Well, 2 pi r is what we're normally thinking. However, if we compare this little one as it gets bigger, that radius is changing. In fact, that radius is changing every kind of step that we move out. So it's almost 2 pi r, but it's in fact 2 pi x when we're spinning around a specific axis. So we have 2 pi x as always going to be the circumference, and the height is going to always be f of x, and that's going to get us our area. And yet again, we want to add up an infinite number of these. And so the general formula for how to go through and find all of these things for shells is going to be, we're integrating from a to b, some 2 pi x f of x dx. So keep in mind this first x is going to be your radius, and this one, the f of x, is going to be your height. And that's going to be the formula that we're going to be using here. And if you're wondering what the dx is, technically it's the thickness of this shape, because even paper, we think paper's, you know, like as thin as possible, but there's some small infinitesimal thickness to it. Okay, this is long-winded and complicated to get us into, let's actually now just set up a formula and be able to solve for this exact volume here. So that's going to be our formula we can be using. Our a to b, those are our bounds where it's crossing. So this one is 0 to 2. 2 pi x is here, and then we need the function's height here, which is 2x squared minus x to the third dx. And the hardest part with these questions is getting the setup, realizing which method we're doing, and going from there. At this point, the calculus of it all is actually not so bad. We can pull the 2 pi out front, distribute the x, antiderivative here, (0 to 2). So we need 2 to the 4th here, which is 16, but we're dividing that by 2. And then we have 2 to the 5th, which is 32 over 5. And then we're thinking 8 over 5, or 8 if we were making it over 5 is 40. So this is really becoming 8 there, 8/5. And so now we just have 16 pi over 5. And that's going to be our exact volume for this shape rotated around the y-axis. Okay, I know a lot. It's overwhelming there. Let's break it down in another question and see if it runs a little smoother, kind of now knowing the general formula for shells that we're going to be using. So this goes back to a question we did last week. And it says, find the volume of the solid obtained by rotating about the y-axis, the region between y equals x and y equals x squared. So we looked at this little sliver before. But specifically, I want us to do this using shells. No, I wanted that to be dots too. So we're spinning that way, and let's think of making a bunch of shells here, and what that setup would be.